To add non-perpendicular vectors algebraically, 1. We resolve all vectors into x and y components. 2. We add the x components, taking into account the direction of each. 3. Add y components in the same way. And 4. The vectors resulting from steps 2 and 3 are perpendicular. Add them as you would any two perpendicular vectors using Pythagoras and the inverse tangent function. So let's add, algebraically, these two displacement vectors. Let's choose north to point that way. This first vector will be 425 kilometers at 12 degrees east of north. There's north, and there is 12 degrees to the east. That's the direction for our vector, 425 kilometers. We're not measuring this out, we're just eyeballing it. We're going to do the same thing with vector d2. The direction for that vector is 28 degrees east of south. Check out our little picture here. South would be straight down. 28 degrees to the east would be right there. That vector is much shorter because it's only 182 kilometers instead of d1 is 425. I'm just eyeballing these at this time. And then I like to ballpark sketch them out so I have an idea of what the resultant is going to look like. We learned how to do that with graphical addition of vectors, so my resultant is going to look something like that. So if d1 is 425 kilometers, I'm expecting my resultant to be 320 kilometers or something like that. In other words, if I get a number like 844 kilometers, clearly that's going to be wrong. To add these vectors now algebraically, that is mathematically, with a good deal more precision than we can graphically, we're going to break these given vectors into components. I've broken this into a northerly component and an easterly component. This one, a north-south, which in this case is south, isn't it? A southerly component and an easterly component. So let's use sine and cosine to find the magnitude of these component vectors. We'll start with the east-west portion of d1. In order to find that, I'm going to need to use the sine of 12. 425 times the sine of 12, 88.4 kilometers east. Remember that these component vectors have directions. They're not lines, so you have to point them in some direction. That's very important when you get to adding the components together. We're going to use the cosine of 12 to find this blue vector. Similarly, use the sine to find the east-west component of vector d2, and we're going to use the cosine of 28 to find the south component of vector d2. Now I have 4 component vectors. Our next step is to add the east-west vectors and get something, and add the north-south vectors, and we'll do that next. We're going to add the east-west vectors. They both point to the east, 88.4 kilometers east and 85.4 kilometers east, for a net of 173.8 kilometers east. And down in the lower right, I've gone ahead and drawn out a vector that represents 173.8 kilometers east. Now the north-south vectors are a little different. One component is 416 kilometers to the north. The other one is 161 kilometers to the south. So when I type this into my calculator, in effect, I need to subtract off the 161, and I end up with a net of 255 kilometers to the north. That's why we say we add them in the vector sense. We don't simply just add them. We add them in the vector sense, which means you take into account their directions. If they both point in the same direction, as the east-west vectors do, then yes, you simply add them. But if they point in the opposite sense from each other, as these north-south vectors do, then in effect you end up subtracting. So we're going to find the resultant vector by using the Pythagorean theorem on those two new legs of a triangle. that comes out to be about 310 kilometers. We're also going to find an angle, which I've labeled in the lower right here as theta, and that will be found by taking the inverse tangent of, tangent deals with opposite over adjacent. That comes out to be 56 degrees. So that would be what? 56 degrees north of east. We're now going to show you that, remember on the previous slide, we drew these out graphically, and there was our resultant. Look at that, just like we were expecting. Now, it doesn't matter that we drew the 173.8 vector first and then the 255. If we had drawn the 255 first, that's fine. We tip to tail it with the 173.8. Notice that the resultant is still the same, but instead of finding theta, we would probably find this angle using the inverse tangent of 173.8 over 255, which would be 34 degrees, but that would be east of north. Let's summarize the algebraic addition of non-perpendicular vectors 2. The process we have described to add non-perpendicular vectors algebraically can be used to add any number of vectors. In the numerical examples here, we have limited our calculations to adding 2 vectors. Let's go through conceptually how the principles apply for more than 2 vectors. So on the right, we have 3 velocity vectors that we want to add. If we add them graphically, they'll look like this. There's v1, there's v2, there's v3. Our resultant should look like that. When we add these graphically, we first find the components of each of these given vectors. Then we add the components. So all of the green vectors point to the right. I'm going to add them, just like that. The red vectors, notice that the first 2 point upwards and the third one points downwards. So we're going to take the first 2 and then we're going to subtract off that third one, giving us a net of a little bit shorter vector. The resultant would look like that if we use the Pythagorean theorem to find the hypotenuse. And look at that. That's the same as the resultant we expected if we added them graphically.